talk about how to predict the products of a double replacement reaction. As always, the key thing that we need to do first is recognize that we're dealing with one in the first place. All double replacement reactions can be recognized by the fact that they will begin with two compounds as the reactants, as we see in the examples here that we have below. Now, to predict the products of a double replacement reaction, we're going to use this neat little trick where the outer and inner ions combine to form the products. Now, as a previous video, this is a lot of information to get written down, so please do feel free to pause the video at this time to get these examples jotted down before we go into the explanation. So with this one, in looking at what I mean by the outer and inner ions combined to form products, it's important to recognize that really all of these things are ionically bonded. What's going to happen in the double replacement reaction is that the positive ion from each compound is going to trade places with the other. Two positive ions replacing one another to form two products leads to the double replacement description here. So to really help us with the product predicting and the formula writing, I came up with this neat little trick. It is going to make ionically bonded products, so why don't we go ahead and acknowledge the ions involved? This is also going to have some further consequences and usage in the future when we talk about these things called net ionic equations, but that's a little bit later on. What happens in a chemical reaction, say this one for example, is that we take some magnesium chloride and some sodium nitrate and we mix them in with a whole bunch of water. And what happens is that these compounds dissolve and separate or ionize, meaning magnesium and chlorine separate from one another and form their ions. Magnesium with its 2 plus, according to what is shown on the periodic table. Plus here. Chlorine with its 1 minus charge. Sodium with its 1 plus. And while nitrate is not found on the periodic table, it is on our polyatomic ion list, and it carries a 1 minus charge. So after we separate these things out into ions, it becomes a little bit more clear as to what I mean by the outer and inner ions combining to form the products. The outer ions are the ones that I'm circling here in red, meaning they're on the outside of our list of ions in this reaction. These two will combine to make one of the ionic products. The inner ions, what I'm circling here in blue, will combine to form the other. Now, even though chlorine is written first here in my list of ions, it is important to remember that anytime we write a compound or a formula, it's always the positive ion that's written first. So by writing out the ions with their charges, it makes the product predicting and formula writing a little bit easier. One of my products is going to be the combination of magnesium and nitrate. Magnesium with its 2 plus charge and nitrate with its 1 minus. So if we crisscross those charges, we end up with MgNO3, 2, like so. Now if we consider the inner ions, the sodium and chlorine here, they'll combine to make our other product, sodium chloride. Now, again, this is not going to give us a reaction that's balanced, or it's very likely not going to give us a reaction that's balanced, but we can still, of course, go back and balance this. This one, despite having a whole lot of moving parts, is really not all that tricky. In fact, just a couple of 2's here will do the job. But the biggest thing I want to get with this one, or want you to get with this one, is that we predict the products by first recognizing the ions involved in the reaction, or reactants, and then combining the outer ions to make one product and the inner ions to make the other. These formulas for the products are always ionically bonded. Now, this little trick works regardless of the reaction in question. Any double replacement reaction can be predicted, or the products can be predicted by using this outer inner method. For example, in my second one here, I can take zinc at a 2 plus, because zinc is always a 2 plus, sulfate at a 2 minus, which, by the way, this is the first time that we really can use polyatomic ions all that much. So be on the lookout for those. Potassium at its 1 plus, oops, and then phosphate at its 3 minus. Again, to predict the products, we take the outer ions and let them make one product, and then we take the inner ions and allow them to form the other. So zinc is going to bond with phosphate. Crisscrossing our charges, we get ZN3 parentheses PO4 2. That's our outer ions coming together. And then our inner ions here form the other, potassium and sulfate, K2SO4. Now, there are a lot of moving parts to this one as well, but predicting the products for this one is also somewhat deceptively easy. As long as we're very, very careful about the inventory checking, and also remembering that it's probably a pretty good idea to balance according to that specific order that I mentioned in class earlier. We should always try to balance our metals first, followed by our nonmetals, then our hydrogens, and then our oxygens. Oxygen is quite literally in every single compound here. Never start with oxygen. They're probably going to work themselves out in the end anyway. For this one, in order to balance, we would need a 3 here in front of our zinc sulfate, a 3 here in front of our potassium sulfate, and then a 2 here in front of our potassium phosphate. Last thing would be a 1 here in the zinc phosphate. Now, I'm more than happy to show the process of how I did that in class or in another video, but for now, again, what I really wanted us to understand with this video is how to predict the products of these double replacement reactions. We should first write out the ions of the reactants and then combine the outer and inner ions to make our products.